Titrations are not a new topic. We've seen them before in the first semester chemistry. You've done a few in lab, but now we have the capabilities of calculating the pH at any point throughout the course of the titration. So we're just going to get familiar with the terminology again and talk a little bit about how to do some of these calculations. So in an acid-base titration, we have two different types of solutions. One is the titrant, that is what we know the concentration of, usually located in the burette. And we have the analyte, which is the solution that we're trying to figure out what its concentration is, what we're testing. We know that when we get to the equivalence point, that the moles of the base are stoichiometrically equal to the moles of the acid. So what does that mean? That means that if it is a 1-to-1 reaction, the moles of acid equal the moles of base. If it is a 2-to-1 reaction, and we know what that ratio is. In order to determine where that endpoint is, we have to add a signaling molecule that is a weak acid or weak base itself, and that is an indicator. And that changes color based on whether it's in the acidic form or the basic form of the weak acid or weak base or of the indicator. The first example of a titration we're going to talk about is where we're using a strong acid and a strong base. If we look at this particular titration curve, there's some things that we can determine. So one is that we are starting with an acid in our flask, and we know that because the pH is less than 7. As we add base, so we're adding sodium hydroxide, which is a strong base, our pH is gradually increasing until we get to where the curve is the sharpest. There's a sharp change in pH. Halfway up that steep portion is where the equivalence point is found. We can tell that this is a strong acid with a strong base because the pH at the equivalence point is equal to 7. Because for a strong acid, its anion is going to be neutral. And so our pH is 7. Once we've exceeded the equivalence point, once we've added more sodium hydroxide, our pH is going to level off and at that basic pH of the strong base that we're adding. Now, if we titrate a strong base with a strong acid, again, we know that it is a base because the pH is starting high and eventually getting low. We're adding hydrochloric acid, which is a strong acid. We can also tell, because our equivalence point again falls at a pH of 7. We're starting high because the base is in our flask. We're titrating with an acid, so the acid is in our burette. Most commonly, what we use for titrations are weak acids with a strong base or a weak base with a strong acid. So when we're titrating with a weak acid, or titrating a weak acid with a strong base, we do get some differences in our titration curve than we saw with the strong acid and strong base. Our initial pH, again, is going to be below 7 because we have a weak acid. We're titrating with a strong base because the sodium hydroxide is being added. We are going to reach a point where we have a buffering region of the acid, the weak acid with its conjugate base. and we know how to find the pH of a buffer solution. We get to the equivalence point, and again, the equivalence point is still in the middle of the steepest portion of the curve. You'll notice that it's not quite as steep as it was with the strong acid and strong base, but equivalence point still falls in the middle. It is not at a pH of 7 at this point because our anion is going to be basic if it's a weak acid. And then as we continue adding base, we'll eventually get to the point where our hydroxide is in excess and we level off again. The initial pH, if we want to calculate our initial pH before we start our titration, it is going to be just like the problems that we saw in chapter 15, calculating the pH of a weak acid. So we're going to need an ice table, and we're going to have to determine what the H3O plus concentration is of that weak acid. So we've already seen how to do these calculations in the last chapter. When we get to the point before the equivalence point, so after the initial pH, before the equivalence point, when we've started adding base, this is going to be a mixture of the weak acid and its conjugate base. And so we're going to have to solve the pH for this using the Henderson-Hasselbalch equation. And again, the Henderson-Hasselbalch equation, that's when our pH equals the pKa plus the log of the basic form over the acidic form. So what we were doing previously in this chapter, because we have a mixture of the acid and the base. There is one special point that is halfway to the equivalence point, or 1/2 of the volume at the equivalence point, where the moles of A minus equal the moles of HA. At this point, that log value becomes 1 and our pH equals the pKa of your weak acid. And so halfway to the equivalence point at that volume, you can find the pKa of your weak acid. At the equivalence point, the moles of the acid exactly equal the moles of the base. So the weak acid has been completely consumed. This results in only the conjugate base being present in the solution. And so we can calculate using the weak base what the pH is at the equivalence point. It's like a weak base equilibrium problem, just like we saw in chapter 15. One thing that you do have to remember here is that because you've added volume into the solution, you have to remember to divide by the total liters. So the amount of acid you started with plus the amount of strong base that you've added to the solution in order to find the concentration. Once we go past the equivalence point, then it's going to be strong base in solution, and we can calculate the pH just looking at the amount of extra or excess strong base that has been added to the solution.